Hello and greetings all. Welcome back to Mathamopoulos. In today's episode of Applications of Calculus, we're going to be talking about the washer method. Now, the washer method is another example of a way of finding rotational volumes that's commonly used in engineering. Now, this in specific is when you rotate two functions around some sort of rotational axis, and you end up getting a hole in this solid 3D shape. Now, the disk method gets its name from the fact that the simplest rotational volume you can create is by taking a rectangle and rotating it around an axis. That would give you a cylinder, or a disk. Now, the washer method is very similar. The simplest type of shape of this kind would look like one of those brass washers, or it would look like Mr. Krabs' first dime from the Season 3, Episode 47 classic, Can You Spare a Dime? So we can't just use the disk method formula that we talked about in the last video. We have to use a new formula that is based off of the same mathematical concept of cutting the shape into slices. Now we're going to take the area of the outer circle and subtract from it the area of the inner circle, and then we're going to integrate that to find the volume of this rotational solid. Now let's just jump straight into our first problem. Find the volume formed when the region bounded by graphs y equals square root of x and y equals x squared are rotated across the x-axis from x equals 0 to x equals 1. Looking at our equation, you can already see I've put in our bounds. Now, the last thing we have to do is find the radius of the outer and inner circles represented by big R and little r. Now, how do we do this? Now, in the last episode, we talked about this idea that the distance from the x-axis to the function is the function, meaning that if you were to rotate it, the radius of that function that you're rotating would just be the value of the function. This is no different. So quite simply, we're just going to use the outer function as our big R and the inner function as our little r. So simply plugging in the square root of x for our big R and x squared for our little r, and plugging that equation into our calculator, we should get a volume of 3 over 10 pi. This is our last problem for the video. This is a bit of a shorter one. Find the volume formed when the region bounded by y equals x squared, x equals 0, x equals 1, and the x-axis are rotated across the line y equals negative 2. Now note this is similar to a problem in the last video. The line y equals negative 2 is parallel to the x-axis. Therefore, this integral is going to be with respect to x. Now, the bounds were given to us. Thank Joseph for that. So we still need to find the outer radius, big R, and the inner radius, little r. So to find the outer radius, we actually have to do top minus bottom. Again, all of these videos I've done have kind of built off of each other in little ways. So big R is simply x squared, the top function, minus negative 2, the bottom function, which would give us big R equaling x squared plus 2. And the inner radius, little r, is simply just r equals 2. That is the radius of the hole that is within the 3D solid. So by plugging in what we got for big R and what we got for little r into the equation and putting it into our calculator, we should end up getting a volume of 23 over 15 pi. I hope you enjoyed today's lesson and hope you come back for the next episode where we will be covering the shell method. That's it for this episode of Mathamopoulos, and thank you for watching. I hope you enjoyed today's lesson and hope you come back for the next episode where we will